Good morning. This is a pretty normal Rotary cowshed for New Zealand, built last year. We're doing a machine test here this morning. First thing we do is to test these regulators, which are actually being used as a safety valve. So we select a vacuum source, vacuum gauge, and we'll put it there. Then we'll connect our Pt2 tube there, and we'll put a little bit of tape over the end of it to block it off. Now we can start the plant with this gate valve in. First of all, we open the vacuum. We open this up to open the extra 2,000 litres up and open this to maximum, and that to maximum because everything's blocked off. add the milk line in. And we've got to remember to connect the bottom up. Okay, no leaks through there. It's good. This is what not often happens with the receiver lid, is it gets sand underneath the rubber seal. So we'll just get that off and give it a clean. It for leaks before we go any further. Right, now that we've got the ACRs tested and the pulsators tested for leaks, for loss, which we had to do back to front because it couldn't turn one on and the other off. They're all on the same power supply. So we take the rings off to give us the cluster air admission through those little holes at the front there. Yeah, this one's there. 50 clusters at about 7 litres per minute per cluster. Should be about somewhere between 350 400 litres of air loss when I go back in the machine room and test it again. Very noisy in there, of course, so it makes things hard to do for you to watch. Sometimes you have to do things back to front. Like I had to put the water into the receiving can later to test for bubbles. I'll go down there now, have a quick look. Yeah, look at that. There's the water level. Not a bubble now. No bubbles at all. So that means the milk pump and the non-return valve are not leaking any air. That's what we want to see. Due to the noise in the engine room during the test, I've decided to show you through the process of writing the report and doing the analysis of the shed elsewhere. So here you see that we've listed 50 rotary, 25 pulsators, 5 MP load, 15 kilowatt motor, Fristron centrifugal 2.2 motor, and down here we've got the vacuum pump speed recorded at 1490 maximum, which draws 9.1 kilowatts, which is under the 15 kilowatt motor size. So it's automatically saying it's okay here, speed and power okay. So we go down to the milk pump and recorded the maximum speed at 2800 RPM. We put water into the receiving can and it showed no bubbles, so we do no bubbles. Test there says okay. We're running at 42 kPa, so that's all okay. That there is saying that it's greater or equal to the standard for the shed, and the standard reserve for the shed is 1350 litres per minute of vacuum, of air at 42 kPa. So we tested the regulators to see what their maximum load was when there was no VSD drive, and it turned out that the regulators were hitting 52 kPa, which is not unusual for these sheds. During the wash they like it to be a higher vacuum to create a better disturbance in the pipelines. So we then tested the vacuum pump with the gate valve shut and no variable speed drive, and we ended up with 2840 litres per minute at 50 kPa. Now that's the level that you test a pump according to its specifications. That 5 MP pump at 1490 RPM is supposed to produce between 2682 and 2980 litres per minute, and it did achieve 2840. So that's well within those limits. So that passed it as an okay on there. So now we tested the with the gate valve shut still. We tested it at the working vacuum of 42 here, and we ended up with 3,570 litres of air per minute going through my airflow meter at 42 kPa or minus 42 kPa. Then we attached the receiver air line that's going right through from the vacuum pump right through to the sanitary trap, and we had a loss of only 30 litres per minute of air through there, which is allowed 50. We did a calculation as to what the pipelines would lose if the vacuum test was done at the receiver, which you can do, but we don't need to at this stage. So we had a calculation of about the same pipe loss of 30 litres through those large 100 mil lines and the gland and the various bends and all that's all part of the calculation. So our airflow start is the same as our airflow with the receiver airline connected. So that's the airflow 3540. When we added the two milk lines, we lost 40 litres of air. So we adjusted the airflow meter until we had 42 kPa again once we took the slide out and attached the milk line and receiver. 40 loss. That's good. So the reason for that is that there's 2 milk lines and we're allowed 30 litres per milk line, adding up to total 60. Then we had the pulsator air line connected. Now that includes the ACR air lines, or vacuum lines, which are above the rams that operate them. And we had a 20 litre loss only through there. That's pretty good. Sometimes you might have 350 or so. So then we lifted up the bail arms. So we got that that black switch we flicked up and then across, down and across, and got all the rams going. And we ended up with 110 loss of air through those rams. So in the pistons themselves, in the tubing, and everything, every part of it, we had 110 loss, and we were allowed for 50 bales, 300 litres loss. So that's okay. Flushing pulsator is then connected, and we therefore don't have the rams up. Now we have them down. So we're going back to this figure of the 4 pulsator air lines, and add the flushing pulsator, and it comes up to the same figure, so there was no loss there. The next thing we did was to introduce the cluster air admission, which are those little holes I pointed out earlier on at the bottom of the clusters, and we do that by taking those blue rings off, and then suddenly all those holes add up to a 540 litre loss, which is within the range of 300 to 600. So that's good. That's an okay on that. Then we turn the pulsators on. Now actually we had to do them in round about the other way, but I have to recalculate it because it was impossible to turn off the pulsators without turning off the rams as well, the ACRs. So we had a 920 loss through the pulsators operating, which is, we're allowed 1750, and that's okay. So then we tested the farm gauge, and we found that it was 1 kPa low reading on every test at 37, then 42, and then 47 kPa. We then went back and set the regulators into the system. Oh, sorry, before that, we did a -2 regulator test with the valves, with those black regulators off. And it usually leaps up at that stage because it is 2 kPa below the 42. So measuring it at 40, it measured 2200. Yes, this is the shed here. So we write in the relevant information up there of what the shed is, where it's located, and this here is the drop test that we did with 2 sets of cups open, what was happening in the receiver when that process happened for about 12 seconds with normal vacuum. Turned 2 sets of cups on, it dropped, it picked itself up by revving up the vacuum pump, and then I shut those 2 sets of cups, and it came over the vacuum slightly as the vacuum pump slowed down and then stabilized again at 40, round about that 42. But because there's a slight difference between the area in the machine room and the receiving can, there's a 0.4 of a kPa difference between we're at the cups, between the vacuum machine room and the cups. So that's why it reads 41.6. So what happened here, it dropped to 39.6 at that point there, and then it went back up to 41.2, held it for the duration, and then when the cups were turned off and no air was leaking, it rose to 43.5 momentarily and settled back to the 41.6 that it was at the beginning. So that's a pass so long as it's within 2 kPa of the normal. Now there's our every pulsator tested, and there's that number 12 there that showed a poor D phase right there. So that's A phase, B phase, C phase, D phase. So A is up, B is across, C is down, and D is the flat at the bottom. And that is the ratio, around about 60 plus, 60-40. Well, it's actually 62 to 38 really, isn't it? And then 41.3 or 4 at the cup is the vacuum. And then there's around about the 55 beats a minute, or cycles per second. Cycles per minute, sorry. And this here is a variation between left and right of 1 only. So there they are, there's all the graphs, and we can see here number 12 wasn't looking so good. Now that then is transferred to the test sheet, and there are those figures there, from there to there, and from the pulsators up to there. And we can see that now is showing all good except for that one little pulsator which marked a cross on there. All that's done automatically for me, and we press save and away we go. We then look at, have to fill in the visual faults, so we look at the shed and see what parts are in it, whether they're functioning properly, and we might put a cross in over here instead of an OK, and then put some information like guidelines not met, or say clusters, something like the hole is too small or something like that, and we would put that in there. Then we go to test summary, and there you see I've entered service pulsator at bale 2324, that's number 12. And you have other options of faults, and you can put a comment on underneath as to whether it was bad or good or whatever, or what to do about it. This here is showing that the regulator safety valve was higher than 2 kPa above, but that is quite normal for those sheds to run at a higher vacuum for wash as a safety valve. Visual faults will be the same as what you saw before, and then these recommendations printed, and then following that we'll have all those graphs and the printout of every pulsator. So there'd be about maybe 7-8 pages, something like that, of information for the farmer, and I might put a pen ring around that there problem, and just draw his attention to it, or put some, say, orange highlighter over it just to bring his attention to it. And that would be the end of the test. Pack up all the gear, wash the teat plugs so they don't cross-contaminate between cowsheds, wash my boots, wash my overalls when I get home, and that's the job done. That shed took about 5 hours work